So we learned about this new type of acceleration, but I wanted to show you where it comes from. Do you remember what acceleration is? What we learned the formula for it was? What's the basic idea of acceleration?
Times gravity.
What did you say? Mass times gravity, that would be like the force of gravity, right? So I'm talking about just acceleration in general. What did we learn that is equal to? In calculus, you learn it's the derivative of something, right? Velocity. So it's a measurement of the rate of change of your velocity, right? Now, a lot of times we'll just write that as change in velocity with these little triangles over change in time. So you're familiar with that, right? That's the good old acceleration that we're all familiar with. We need to learn about a new type of acceleration that it's a little bit different. So this type of acceleration is only coming from a change in direction. And so in order to do that, let's look at a circle. And so if you are traveling in uniform circular motion, that means you're spinning something around. I'll get my thing out again just to let you know. So it means you're spinning something around and you're going at a constant rate, somewhat constant rate. Okay, so it's not like you are applying any sort of angular acceleration to this. It's just a constant speed, but it's constantly changing direction too. Look at that. And if it breaks, it travels off tangent to where it was traveling, right? And you learn about a tangent line. So at the top, let's say that it's traveling at a velocity v, right? And we could call that vi, the initial velocity, because that initial velocity has some direction to it, right, which is tangent. And then you have some final location. Let's just make it interesting. Let's make a final location. Where do you want it, 30 or 60?
60.
All right, let's do 60 degrees. So right here we'll have a final location. All right, now this is our VF. Now, in order to look at our initial position, we're going to go up like this, and we'll get to something we could call RI. And RI could just be your position vector to get to your initial position on the circle. And then we're going to have the same thing. So these I's and F's, the I stands for initial, and the F stands for final. Now we have some sort of a final location on the circle, right? And in that amount of time, we traveled a certain angle there. So we can put an angle right there. And that angle corresponds to a certain arc length right here. So we traveled a certain amount of angular displacement in that amount of time. All right, so we're going to keep going with this. I wanted to show you guys, if you look at just these vectors right here, so let's kind of take these vectors and redraw them. So I'm going to draw it like this. Now I'm going to take one vector and put it on top of the other vector. So it's going to look something like this. So you would agree that the first vector is kind of like this, right? For my velocity? Good?
Yeah.
The second vector is coming down like this. I'll try to do this nicely. Okay. VF. Okay, now in terms of the position, you're starting off like this. RI at that position. And usually we draw vectors tip to tail, but in this case I'm just going to draw them tail to tail. And then we have another one coming up kind of like this. Okay, so RF. Okay, good so far? It's going to get a little bit intense here, but I want to show you where this acceleration is actually coming from. So the next thing is we could draw a little arrow here. Now this would represent my change in velocity. You good with that? So you went from a certain point to a certain point, like the tip of that arrow to the other tip. So I could say, okay, that's my change in velocity. And I could do the same thing for my position. So I can start here and end here. Okay. And I can call that my change in position, delta r. All right, now the other thing we're going to want to do is figure out what this angle is. This angle that I drew right here. And so that angle is going to be, so let's write down theta equals, how would we find that angle? What did we say that this was? We set this to be what? 60, right? 60 degrees. Now this right here is 30 degrees. So what would theta be? 30. Now there's a couple different ways we can do that. We can just say, okay, well that's equal to whatever the angle is at our initial position minus whatever that angle's at the final position. And so at the initial position it's 90, right? 90 degrees minus 60 degrees, which we already said was 30 degrees. So that's kind of what was going through his brain when he said that, I think. There's another thing you can do. You can do the same thing for your angle for your initial velocity and your final velocity, right? And so the same thing would apply if you had the angle for your initial velocity and your angle for your final velocity. It would be a little bit different though, because if you look at the angle of this initial velocity, what would you say the angle of that initial velocity is, that arrow up there? 0. You see how it's kind of flat, right? So this would be pretty much 0 degrees. And then what would you say the angle of this final velocity is then? Negative 30. And notice how those two things are equal. So it doesn't really matter which ones we're looking at. And so that's kind of a cool result. What that allows us to do is say that these guys are pretty much similar triangles. And so have you learned about similar triangles? And it's specifically side angle side. So now, because it is a similar, those two things are similar triangles, there's a reason why you learn some geometry. There's a couple other things we have to keep in mind. In this case, we're talking about uniform circular motion because we're only looking at the changes in direction. So we are going to assume that there's no angular acceleration. So the only acceleration that could exist then is just from the change in direction. Let's write that. So pretty much what I'm saying then is that the magnitude, not necessarily the direction, but the magnitude, so we can use like absolute value symbols, of our initial velocity is equal to the magnitude of our final velocity, right? And sometimes we use little vector symbols because these are vectors, and sometimes people do the double bracket to distinguish maybe the difference between that and absolute value. But the idea is that the magnitudes are equal because in other words, the lengths of those vectors are equal, of those arrows, because they are at the same speed. And then down at the other one, would the length of these r's be equal to?
Yeah.
Because it's a circle, right? That's just the radius. So you look at the same idea, and you can kind of look at these position vectors where you have this initial position vector, the magnitude of it, not necessarily the direction, but the magnitude of it is equal to, so based on how far it is from the center, is equal to the RF, here we go, there we go. So, and that's just pretty much because it's the radius, right? It's the radius of a circle. And we're talking really about circular motion. All right, so then last kind of step here, it's not too bad, is, do you remember when we have similar triangles, you can look at ratios being equal, like you can set up a ratio equal to another ratio, you're pretty much setting up a proportion. So we can say that this change in V, so this change in v, and these are all vectors, over v is equal to, so change in v over v is equal to change in r over r. Because we said that the initial and the final were pretty much the same, right, for r and f. So we can rewrite it simply like that. And then from there, I'm actually going to use a different color, red here. I'm going to do the same side. We have an equation. We're going to do the same thing to both sides of the equation. And you'll see why in a second. But is it possible that I could divide both sides by delta t? Can I do that? Like mathematically, and that's okay, right? Yeah. So I do the same thing to both sides. And if you do the same thing to both sides, then you'll notice something. You'll notice that this part right here, okay, and this part right here, that kind of means something, right? And so you'll notice that we already told you what that was in the beginning. Remember, we said acceleration pretty much is this change in velocity over change in time. And now we kind of found out what that is. So what I'd like to do is take that v and multiply it up to the other side. So we're going to multiply both sides by v. And so this v is going to cancel. This v is going to cancel. Right? And so pretty much v over v is 1, right? And we got a v over there. So let me kind of rewrite this a little bit. So I have delta v over delta t, right, equals delta r over delta t. And then I'm going to also say that that's also a v over r. Okay. So that's kind of a little bit more pretty, but it's going to get a lot more wonderful here in a second. So you look at this, and we said that that was just acceleration, right? So acceleration equals, now based on everything we've done so far, this is the acceleration only because of a change in direction. So we're going to put a C there for the centripetal acceleration. And then you'll notice that a change in position over change in time, this thing right here, does anybody know what that is? When you're changing position over time? What does that turn into? Velocity, right? And now you could write that as, so v, right, is equal to your displacement over time, right? And you could say that that's equal to delta x, let's say, over delta t. Or in this case, we're not specifying the x direction, we're just using the r as our position. So we're familiar with this as well. And so because of that, we can plug that in for here to just be v. And so now we have, this is v, and multiplied by another v gives us what? What's v times v? V squared. So on the top you have v squared, and on the bottom you have r. So the centripetal acceleration is v squared over r. Now that's the acceleration that is only coming from a change in direction. Only coming from a change in direction. Change in direction. All right. It is not coming from a change in the magnitude of your velocity. It's only because you're changing direction. So we have this new form of acceleration. And because of that, if you remember F equals ma, right? Now, we learned that, but we're going to have a new form of F equals ma. So this is F net equals ma. So we could do, let's say, F net, right? The net force is equal to ma. If you want something to accelerate, you need a net force. But we have a new form of force, let's call it Fc, which is called the centripetal force, equal to MAC. All right, and so this right here is important. And we said that that's equal to then mv squared over r, because we can plug in what we just found out. And we can also relate that to, do you remember the angular velocity? So if you look at the regular velocity is equal to the angular velocity times the radius. Do you remember that one? And we plug that in on the top here. What we get is mv squared over r, and we're going to plug in m omega r squared over r, right? And that is just m omega squared r squared over r. And then one of those r's cancels, and you're left with m omega, that's your angular velocity, squared r. Okay, so this stuff right here is equal to your centripetal force, and your centripetal force is usually equal to something that's supplying it. What's one thing that can supply the centripetal force?
Acceleration.
Like on your way here this morning, it was super icy. What was supplying your centripetal force as you were turning your vehicle? Friction, I hope. Otherwise, you're not able to turn. Imagine you're on a super icy road and you start to try to turn. It's not really going to happen. The only reason you can turn and send yourself into circular motion and have some sort of a turning radius is because there's got to be some sort of a force holding you into the center of that circle. And so this centripetal acceleration is always acting towards the center of the circle, which means your centripetal force is also always acting towards the center, but the centripetal force is not really a force of its own. It's really just a new type of net force, right? And it's supplied by something. It's supplied by normal force, friction, tension, gravity, right? Anytime you have circular motion, there's got to be a reason for that happening. And so usually we set this equal to something that supplies it. Okay? Some other force is supplying the centripetal force needed for something to travel in a circle at a certain velocity. Now, this is all pretty much uniform circular motion. We can get a little bit more complicated once we start adding angular acceleration too. Because now let's say you're at a stoplight and you're putting your foot on the gas. Now you're starting with 0 angular velocity and you're reaching a new angular velocity. So now we have torque, and torque is angular force, but that's a little bit different, so we'll get to that. But this is the basic idea of what we're talking about with this new type of acceleration and centripetal acceleration and centripetal force and angular velocity and all that stuff. So I think we're good. It's a bucket, and if this breaks, it's going to be kind of messy. But I just wanted to illustrate something. So as we spin this, and it gets to the top, clearly right about here we're about to spill water out of it, right? Now, if I spin it all the way around, you would think that when it gets to the top, all that water is going to come straight down at me. I mean, that's what logic says. But if you spin it fast enough, it might be able to do it. So, I got to practice this.
Really fast.
Okay, you ready? Look at that.
Darn.
See that? So you saw the water was upside down there for a second. Now, you would think that there's some sort of centrifugal force pushing the water out the whole time, right? And so really what's happening is as you go in a circle, what's holding this water? Imagine that the water is an object, right? It's a fluid. It has mass to it. The mass wants to flow. It wants to fall out. What's holding it in circular motion? What's holding the water in circular motion? What force?
Torque.
If it wasn't for what, the water would go everywhere.
Friction.
Not friction.
What does the bucket provide?
Normal force.
The normal force. So the force of this bucket, imagine guys, the water wants to go where it was going, and you're constantly changing the direction of the water. And so as it gets to the top, its velocity is kind of like this. And really the only thing preventing it from going all over the place is the normal force of the bucket. So what's providing the force holding that water in circular motion? It's the normal force. It's supplying the centripetal force. So pretty cool demonstration. But now, you all know that if I were to go super slow, then it would definitely fail. But I'm trying to push the limits of physics here. No, I heard it come down just for a second, and then it got caught on the way back. Anyway, so that's one thing you can do. Now you can also use more water. So the more water, the more force. Now, so one thing to note is this bucket, what's causing the circular motion of this bucket?
You.
Me. But what's preventing the water from going all over the place?
The normal force.
The normal force from the bucket. So I'm causing the centripetal force with my applied force, and then you have the normal force from the bucket preventing the water from going all over the place. All right, here we go.
Hold on.
So some people call this the centrifugal force, the opposite of like the centripetal force. All right, here we go. All right, so I have more water in here. This bucket's almost full now to the brim. Now, I need to, if this breaks, if the handle breaks, it's going to be a mess. I'm telling you right now.
We hope it does.
This is an improvised demonstration. Did it. That's what I'm talking about. So now we can have more mass and we can have more velocity. Those are some factors that affect the centripetal force. What's the last factor in this formula that we could mess around with?
The radius.
The radius. So I could try to spin it in a smaller radius, but that's not going to work very well.
No, do it.
Okay. I had some fall out. Did you see that? I had it spill a little bit, but okay. So I had a smaller radius, and that's another thing.
Do it slower, but like all the way around.
No, you just want me to get soaked
Okay, no,
up here.
do it really, really fast and break the handle.
No,
Do it
that
back
results
there.
in me messing up
Do
still.
it back there. You won't miss
No.
anything.
All right.